thanks everybody for joining. So, we'll kind of run this panel like the previous ones. We'll have some brief introductions from the panelists. Obviously everybody's order is kind of mixed up, so I'll just call on sort of the first person I see, and then they can kind of go in the order that they show up. Everybody will give a brief introduction. I think pretty much everybody here has a video on the AHUG channel, so please go watch those and learn more about kind of their background and what they've been working on recently. Then we'll go into the Mentimeter questions. We do have the link that's in the chat here. Obviously you can use the Q&A if you have a clarification question, but we do have some kind of seed questions, and we'll go through your questions for the panelists to talk about and answer. Okay. So just going in my list, I'll start with you, Andrei.
Hello, I'm Andrei. I'm a final year PhD student at Bristol with Simon McIntosh-Smith's group. My work is on modern high-performance architectures, and I'm focusing on vectorization and SVE in particular. For the past few years, I've led the efforts of our group into using ARM for HPC. And the video I've submitted is a summary of 2 research papers that we published this year. Both of them look at SVE. One of them is from the point of view of vectorization and how that affects the code that gets generated and run in various mini apps. And the other one is from a cache usage perspective and the impacts on cache of vectorization.
Jeff, you're muted.
Oh, sorry. Go ahead, John.
Myself?
Yes, please.
Okay, my name is John Stone. I work at University of Illinois, and we developed 2 flagship molecular modeling applications, NAMD and VMD. And my talk was about our adaptation of those software packages to run on ARM platforms, and in particular, GPU accelerated ARM platforms. And so we used the Wombat cluster at Oak Ridge National Laboratory and did some early evaluation there. And I just had my first experiences writing hand-coded vector instructions on SVE using the new Fujitsu processors that they installed at Oak Ridge. And so I was just going to share my experiences with those works in progress.
Thanks, John. Okay, next on my list, I have Roxana.
Okay. Hi, yeah, I'm Roxana Rusitoru. I work for ARM in research, specifically in the machine learning group, and I've been looking for the last year at ML on CPUs, primarily data center training. And my talk was actually about the deep learning stack available for ARM. I know there are some questions in the previous panel that I'd definitely love to address.
Okay, great. Let's see. So next, Sai.
Hey, good morning, everybody. So I'm Hammond. I work out of Sandia Labs in New Mexico. My beautiful New Mexico is behind me. Doesn't look like that today. A couple of things in the talk. So we worked really hard on Astra, which we showed you guys the last couple of supercomputing events. So there's a few updates on that in the talk. We developed a software stack called ATSI there, which was designed to be like a curated stack for HPC on ARM, where we were able to put a lot of optimizations in there. So that's a sort of contribution to the community, and it's open, everybody can get that. And then we started working this year on A64FX test system. So lots of results, early results from that, show you some of the benefits there with high bandwidth memory. Some of the benefits of vectorization, but it's not a panacea. There's some challenges ahead there with different compiler combinations and things that we show in the talk there. And then just a quick plug there that ATSI is also now ported to A64FX, and there's just some details of where you can go find, an SVE HBM optimized stack there, which is working with all the compilers that we show in the talk. Thanks, Jeff.
Okay, thank you, Sai. And Stephan.
Hello, my name is Stepan Nassyr. I am a PhD student at the Juelich Supercomputing Center in Germany. And my topic I'm working on is also future ARM-based supercomputers, and I'm investigating what consequences are of increasing the vector size, and if this also means that other architectural values needs to be increased. And something I've been working on recently is this porting Bliss, which is a BLAS-like library to SVE, ARM SVE. And yeah, dense linear algebra is maybe not particularly exciting for some, but it is an easy thing to look at, something like consequences of raising vector values. And yeah, the port seems to be working well so far, and we see pretty good results.
Great. Yeah, there's actually I think there was a comment on your YouTube video that asked if we would see any A64 effects results around or after SC. So you can confirm or deny that if you like.
We are targeting the end of this month, like I said in the
Mhm.
video, for publishing our results on A64FX. And the results look pretty good. And if you have access to A64FX, you can actually just take our code and run some tests.
Okay, great. We'll look forward to that. Well, thank you everybody for being here. So I'm going to share my screen and share the panel questions here. So hopefully everyone can see those appropriately. So we have a couple seed questions, and then if you have questions, go to this link right here. Use the code 5431998, and it'll kind of ask you to answer these questions, and then you can also pose your own questions. So just to start, and just to point out that these are comments that some of our attendees or panelists have put in their thoughts here already. But where have you seen a change in the quality of simulation results when you're using some of the latest ARM-based CPUs? So that could be either ARM v8 in a TX2 type system, or with A64 effects.
Or maybe I'll jump in, Jeff. So what there's kind of different ways of interpreting that question, right? One of them is whether you get exactly the same results as x86, and I think the answer to that, is no. But you don't get the same results across different x86 architectures if you use different vector lengths. So it is different. Is it high quality? I would say that we don't see necessarily high quality, but we don't see worse quality. We see very similar results if you've got the software stack right and the code is actually well written in the first place. There's been some challenges, I think, where we've moved code from x86 and it's relied on, say, the Intel compiler on Intel. We've had to make a few of those changes, but they've been fairly small. So I would say the path to moving from a non-ARM architecture to an ARM architecture, it's not zero effort, but it's pretty low effort. And you should end up getting pretty reasonable quality results, whether using ARM compiler or GCC. It should be pretty similar.
I'm going to address this from a slightly different perspective. So a lot of people are saying software accessibility is something that has changed. And I think if we look back over the past few years, it definitely has. When the Isambard system was first installed, which was one of the first systems to use ARM v8 in production, a lot of the applications that people wanted to run on the system didn't support ARM platforms. At the very least, the build systems weren't aware of the platforms, and minor tweaks were required. But today, everything that we run, everything our users run, just works on ARM out of the box, and it doesn't make a difference if you're using GCC on Intel or on ARM or LLVM, just the same. Most of the applications that we have seen now have built-in support for ARM platforms, and if you're just a user, it definitely does not make a difference, which I think is a great improvement in support.
So another vote for software accessibility there. Yeah, I think this, like Sai says, that it depends on what you're looking at and what you're comparing against. So, are we comparing? I think specifically this question was meant to say comparing ARM versus ARM. What do you see as the changes there? And definitely, looking at our last panel, it seems like with the easy build and the SPAC and Open HPC, I can see where a lot of people would vote for the software accessibility. You would hope that you'd have very few people that would vote for fidelity or results, because that's saying that potentially previously your results were not high quality on a previous ARM platform, which I don't think is the case. Okay, are there other thoughts on this question, or?
I would just say that our experience was the same as Sai's. I mean, really, our results in terms of accuracy and fidelity and so on are basically the same on the ARM hardware as what we had on comparable platforms. So no surprises, really. I think it boils down to the portability of the software you started with.
Mm-hmm. Great. Okay. Oh, go.
Yeah, I just wanted to say that as someone who has actually have adapted a couple of packages for building with easy build for ARM, I have seen that it is usually possible to just compile anything without changing anything. And in cases where you have to change something, it's very small changes that are required.
Mm-hmm. Okay, great.
Jeff, I'd like to say also Guillaume is here. Guillaume is here as well.
Okay.
He just joined as well.
Let's see if we
he's
can
here.
add him to the panel.
No, he's in a panelist.
Okay, great.
Let's say hi.
Guillaume, would you like to speak to the first question here, or give a brief introduction?
So, can you hear me?
Yes.
Okay. Okay. Oh, I'm really sorry. I don't know what happened. I couldn't join.
Oh, that's okay. That's I think we have you as admin, so we were assuming you were the super user. But no worries.
Okay. So excuse me. So what's your question?
I think the question was, have you seen any changes in kind of between the different generations of ARM hardware and software in terms of, has it improved your simulation results? Have you had additional challenges with, say the more recent A64FX hardware or with associated software stacks? We're just trying to see what's the current state of the art in terms of actually running applications.
For me, the main the big change with SV is VLA. Of course, a lot of code that you can see, for example, in GROMACS, lots of code make the assumption that you can manipulate arrays of SIMD vectors because the SIMD vector size is known at compile time. But this is not the case with SV. So it's I think it's well, it's difficult, and it's a lot of work, to change such a code like such a code like GROMACS or a big code base like that. So it's a huge challenge.
Mm-hmm. Great. So VLA kind of enables an easier porting process for newer systems.
So sorry, I didn't hear the question.
I was just going to say, it sounds like you're saying that VLA greatly reduces the complexity of porting to new architectures.
You think VLA is the porting to new architecture? That's what you say? Sorry.
No, I that's okay. I was just saying, it sounds like the VLA has been very beneficial for porting new applications or existing applications like GROMACS.
Oh, okay. What makes you say that?
I was trying to say, is that what you're saying, or are you saying that it's actually more complicated?
No, it's more complicated.
Right. Okay.
No, it's more complicated. Yes.
Right. Okay. Thank you. Sorry. Okay. So this is for all the panelists. You know, what type of ARM-related hardware or software are you most looking forward to drive the next generation of scientific progress? We have a couple suggestions here from attendees and panelists. You know, maybe here this is a good place to pontificate on SD plus ML. Roxana, do you wanna start off with this one?
Oh gosh. Well, it works. So SD plus ML. I mean, okay. I see they're kind of flexible machine learning training. I'll be honest. I don't exactly know what flexible machine learning training means. I mean, it changes every 2 months anyway. In terms of SV and the A64FX, what I can say is TensorFlow does build. I have built it myself on ARM. And there are already recipes out there for building with and without. And there have been actually a lot of efforts also, not just from us, actually a lot from Fujitsu and Recon. And there are a lot of kind of popular libraries and tools available, primarily around the, for example, optimized mathematics libraries. So take, for example, 1DNN is available with for SV as well, and Kaibiaku. I cannot speak whether they are full support, as in 100% of. I cannot speak to that, but there's already quite a lot of progress being made every single month. So that is, as I said, there's already something out there. And yeah, I mean, to build things, kind of just build things and have things kind of get started with, there are already a lot of guides also. In my talk, I put some concrete links in my slides quite close to the end, so people can just kind of go and get for things like recipes. And they're already kind of Docker recipes, because people like to kind of give you some Docker guidelines. And the other one was actually now also have some nightly kind of or some kind of snapshots already of pre-built images. So things are out there.
Great. Does anyone have any? There's a lot of hardware things I see. A64FX revision 2. Does anybody have any specific software things that they see as being very exciting in this space?
I just have a question. What's A64FX2? Because I love to see that first before we can comment on the software. I just love to see one.
Well, we assume that it'll probably have a different name, but yeah, the next generation of that type of hardware. Does anyone have any of the panelists have any thoughts about the computing in memory or computing in a network for algorithmic approaches? I don't know if anyone on the panel has experience with working with that with ARM hardware, like the Bluefields, or Mellanox has kind of, you know, their embedded ARM cores in the network.
Well, I think our interest, just speaking, this is speaking for me, not for the lab, but I think, it's a view that's shared by a lot of people in the teams that I work with, is we're interested in ARM because there's a whole ecosystem of hardware there. And I always think about this as like the ingredients for your soup, right? And you can make a different hardware soup for all the different problems that you've got. So you can have different soup on Monday to different soup on Tuesday when your workloads are changing. So that's really interesting because it allows us to bring in different acceleration pieces for the different kind of workloads that we've got to deal with here at the lab. And an absolutely ton of those, right? And not all of them work really well on any one particular system. So what we end up doing is sort of taking a system that works averagely well on everything. So it opens up an opportunity for us to have these sort of more optimized systems for specific workloads. And we're pretty explicit that we've got a lot of workloads that have got very nasty latency properties in memory, wandering around memory, chasing lots of pointers. And we've got stuff in the network where we're wandering around doing relatively small loads over the network to file systems. There's a whole massive possibility here of having some kind of active memories and active networks that don't require us to read in bulk loads of data and throw an absolute ton of it away just to find one of these operands. Think about it like, a search in memory. Go find me a key that matches, 1, 2, 3, and it wanders around in a hash table in memory and finds that stuff. ARM's really well positioned, in my opinion, for that kind of stuff, just because it's got this ability to mix and match lots of IP. So we're super excited about what we might be able to do with that in the future. Now, we don't have all those IP blocks available, and we've got to find integrators and implementers for some of those IP blocks, and people are going to bring it in and validate it. But I think that will change. That I think is the direction of travel. Some of that might be flexible stuff like FPGAs or coarse-grained arrays of functions and won't necessarily be fixed ASICs. But the future to me looks like a lot more dynamic. It's a lot more dynamic in what the hardware might look like. And I think that will lead us down a road where our applications will have to be a lot more abstracted from the hardware that they're running on. We need lots of good interfaces, and we need runtimes that will essentially take that, convert it to the hardware. So I think the future, we're sort of heading in this direction. I think a lot of people in the industry are thinking about that. But ARM, I think, is well placed for it just because that's been its model from the beginning. So that's one of the reasons why we're really excited, and we keep spending a lot of time trying to make sure that we're ready to go on ARM hardware.
Great. So what you're potentially excited for is specialized accelerator hardware that's that's not necessarily SVE or a GPU type accelerator, but something that's more application specific.
Yeah, I mean, I think about a node as maybe it's going to have, I don't know, 4 different accelerators. You think you've got 4 little slots. So maybe you do put a GPU in there, right? Because that works for a load of your workload. And maybe you put an FPGA in there, and that we can use those things for different phases of our physics as we're running, or different workloads that we load into the machine. Probably not going to have all of those, firing all of the time because we won't have the power budget for it. But the ability to actually put these different types of hardware and mix them in the nodes and have good connectivity and good memory subsystem support. I think you can almost see that coming, right? With all these new links like CXL and everything, you can see all that. But the implications for software are pretty drastic, right? You need very good interfaces, and you need some really good runtimes. You can't be down in the weeds writing assembly because then you're going to move it to another machine and that accelerator won't be there. So we're busy doing lots of abstraction and trying to get good, solid, concrete agreements of APIs between the different science participants and stakeholders in the community. So it gives us a lot of that flexibility moving forward. And if we can really get to that flexibility, then we really can do mix and match on different hardware systems as we move forward. And that really opens up a massive area for very, very strong optimization for processing, memory, networks, storage. So that stuff we're really excited about that.
Excellent. Does anyone else have any comments on anything they're excited about, or anything that they think is currently missing?
I think we'd like to see next generation nodes that have tighter coupling between processors and GPUs. We've been very happy using GPUs as accelerators for the heavy lifting in our molecular modeling applications, but one of the limitations of the existing platforms has always been PCI Express based communication, which has very high latency. As you may know, we do time step based simulations where we want to simulate biophysical events that occur on timescales of microseconds to milliseconds, but the step size in simulated time is in femtoseconds. And so that means we end up taking huge numbers of time steps to get there. And although we have made the computational kernels very performant, the more successful we've been at that, then the more the latencies incurred from commodity interconnects like PCIe have become an impediment to further performance. And so having a future platform that sort of eliminates some of those bottlenecks and particularly architecturally unavoidable latencies would be great. And as far as I know, PCI 4 and PCI 5 and so on, while they increase bandwidth, they're not really addressing anything about latency as far as I know. And that being the case, that would be something we'd like to see a way out of.
Right. So something that is, more like a SMX, style integration, or maybe even a CXL type integration in the future with something that's very low latency.
Yeah, I mean, you could imagine putting an ARM processor, a Mellanox NIC, and a GPU all on one board and find some way to tie them together that bypasses traditional latencies. I mean, that might be costly. I mean, that's one of the outcomes of custom hardware is you're giving up some of your commodity price break, probably. That's what Sai said, I think is true of many application domains. There are great opportunities to do new things, but we're going to have to pick and choose very carefully which commodity things we can live without, and what are we willing to pay for, because it's for sure not going to be free. And so that is an interesting question. Can we get rid of something like PCIe, or would that already break the bank? Would we as customers be willing to pay for it, to get the reduction in latency? We'd have to know what the numbers look like.
Okay, great. All right, well, we'll move on to the next question here. Okay, so this one was kind of forward ported from the first panel because it came up there, and hopefully I wrote this correctly according to the way that it was stated. But the question was, if you're testing an application, and I think this is probably speaks to people who have worked on multiple systems. So definitely like Sai and John have worked on a lot of different x86 and ARM systems. Can you speak to differences in terms of performance and also programmability for AVX versus SVE?
I'd be happy to speak to programmability. I haven't had much of an opportunity to do hardcore performance analysis on SVE yet. We just got access to the new A64FX processors that are in the Oak Ridge Wombat cluster in the last few weeks. And so I have had an opportunity to take existing hand vectorized kernels that I've written in SSE, AVX, AVX512, and make SVE adaptations of those, also hand coded. And I have compared, how they did versus stock C++ loops, and they do very well. They outperform anything the compiler was able to do by itself. There may be more compiler magic that I could get more out of the stock C++ loop, but this is the early stages. But I was really after getting more deeply involved in writing SVE by hand, because there are a lot of things that most compilers are unable to vectorize effectively. There are things that they don't understand, or things that they're not willing to do because they can't prove loop carried dependencies or things like this, and only the programmer can either annotate or help the compiler with those things. The other thing is the compiler doesn't always know what the typical vector lengths are going to be, or how many loop counts something's going to have. And so it might make unprofitable decisions. So it turns out that for some of these kernels, it's just better for us to write those by hand, especially if we have a lot of very low hanging fruit. They're very small loops. They might only be 3 pages of code to do something pretty sophisticated. But if we do that in a hand vectorized loop, it's well worth it because we use it all over the place. So to give you an example, in VMD in my application, we have lots of loops that process what we call atom selections. So these are text-based selection language, kind of like a Google search for different parts of the atomic structure. Well, this ends up grinding through whatever size the graph is for the atomic structure and the different nodes and things it has to reference. And the faster that code is, the faster everything else that depends on that is, including the setup time, say, to launch a GPU kernel to calculate something using that as a parameter. And, you know, at some point when we have enough flexibility on the GPU, or we have enough memory for all the data structures, maybe some of that will move to the GPU, but in the intervening time period frame, all that stuff still remains on the host for good reasons. And so making that faster is a big deal. And so I went and ported some of those. And my observation would be, you know, compared to one of the things that's sort of annoying about the legacy architectures that we've been dealing with for 20 years is that vector instructions were put in, you know, originally with a very small application domain as their reason to exist. So you start with MMX, it was video transcoding. I used to work in video encoding decode, so I was familiar with that way back in the 90s. We got MMX, then SSE. That was sort of another sort of graphics orientated add-on that was intended to provide a little more oomph for games. You know, these were not fully featured vector instruction sets. They solved a problem that we had at the time. One of the things that's a lot better, I think, about SVE being realized in the form that it has been is that it's sort of trying to solve it as a whole, not just a piecemeal specific problem, because the way that this has been done in the industry before has had what I would sort of describe as a whack-a-mole concept of, you know what, we need to solve that application this week. Let's go add a few instructions for that. And I think that's led to a little bit of chaos in the design of some of these things. It leads to a lot of sharp edges when you write code using those instruction sets. So for example, you get weird things like in one vector subset, you can do all the operations across the entire vector. In some other subsets, well, you can only do that on a half a vector at a time, and then you have to shuffle the vector to do it to the rest of them. Things like that are very non-intuitive, and they're very, very hardware specific, and that creates a lot of chaos when you go read the code. You use it, why are they flipping the vector on? What's all this shuffling for? Oh, on that machine, they can't get to the they can't do it that way. They can't do it to the whole vector at once. So having that solved and more uniform has been very nice in my interactions with SVE. Having actual reduction instructions and things that work across the entire vector and not just a piece of it. Having it being length and agnostic, having predicate registers as a fundamental concept makes it a lot cleaner to write things that are complex start and end loops, things that are alignment dependent or problem size dependent, which have, where you, for various reasons, can't make things or don't want to make things vector length multiple or vector length padded, things like that. And so I found that to be very easy to use with the SVE type approach. And so I'm a big fan of that. It makes the code a lot simpler to read. So then the question remains, what does the performance look like? So far, it's been good versus, the same platform versus itself. But I have to be honest, I haven't gotten to the point where I would want to say anything about how it compares to any other hardware. I just haven't had the time yet. So anyway, thank you.
Got it. Great. Thanks for such a comprehensive answer, John. And we actually had some follow-up questions to your comment, which I think were answered in the chat by Sai. Basically asking, what do you mean by writing SVE by hand? And thank you, Sai, for answering that.
Yeah, in that case, all I just meant was writing the intrinsics and not hoping the compiler does it for me, because of course the compiler will do what it can too.
Right. So giving it a little bit more help. Do any of our other panelists have any experience with this question that they'd like to speak to?
What I can add here. Oh, go on.
Sorry,
go on.
no, go on, Roxana.
Okay, no, but my only comment is, I agree with what John said. The only thing to keep in mind is some libraries. So if you, for example, not porting a full application, but porting an existing library to it, we have seen, obviously, there's people making assumptions about the vector length. So there can be some challenge around that. So If you can write from scratch, that's absolutely amazing. Life is easy. If you're trying to port an existing library, which is what happens for us in the land of ML, it may not be as trivial, but it is definitely possible. It's definitely doable, and we have been doing it. Go on, Andrei, your turn.
Yes, I wanted to say from an auto vectorization perspective. So when you have high level code and you let the compiler do vectorization, we've seen compilers that are currently available vectorize basically as much as they can vectorize with AVX 512. So with Neon, that wasn't always the case. When you work with something like a ThunderX2, there's a lot of code that can be vectorized with some variant of AVX, but not necessarily with Neon because it's a much more restrictive instruction set. But with SVE, with all the codes that we've worked with, all the code that was vectorized on AVX was also vectorized on SVE. I also don't want to speak too much of performance at this point because that is still quite early. So we have done some experiments with A64FX. If you've been to one of the other sessions, you'll have seen a talk by Simon showing some of the results we had. These are sometimes good, sometimes bad, and I think the compilers are now at the stage where they can use SV to vectorize loops, but they can improve in the quality of the code they generate. So just because they generate vector code that uses SV instructions doesn't necessarily mean that they will get as good performance as they could. So there is some room for improvement there. But I think it's a very good start that we can vectorize these loops at all, but whereas we couldn't before on Neon.
Mm-hmm. That's a very good point. Does anyone else, Guillaume or Stephan, do you have any thoughts you'd like to share on this particular question?
Yes, well, for Bliss kernels, to make them vector length agnostic, not really a lot of features of SVE have to be utilized. You just write a normal kernel with your FMLAs, and then you determine the size of it at runtime, and then you can, it's basically the vector length agnostic part happens at a higher level than assembly. But I have also noticed what John mentioned about this permutations required on AVX. This I have particularly have seen with complex numbers computations to load them and to calculate with them. It's much easier to do with the Arm ISA and SVE, and but also as well with Neon as well. With Neon as well, and SVE. And I think RV8.2 also has those complex, specific instructions for complex multiply add. And this is also something that we are looking into, if this actually offers performance benefits. And so far, I like what I see.
Great. Okay. So I think we'll move on unless you know, I see here we had another question or I guess a Q&A kind of a post from CR. Apologies if I mispronounced your name, but the clarification on the GROMACS, it has difficulties with the VLA. So I'll just leave that here in the Q&A if you want to read through that, since that's a really nice explanation. Okay. Moving on. Not quite as many answers here as I would expect, but this is you know, every session has to have this you know, question that is meant to kind of raise the ire of our panelists. If AI and numerical simulation are both increasing in importance for users, do you think ARM systems embed enough AI-related capabilities? And we're interested to hear your thoughts from both the ML side and the HPC side, or viewpoint, I guess. Roxana, this question is kind of I wouldn't call it an attack, but you know, it's
I was like, does anybody else kind of take the mic and go ahead of me? So okay, so I think it depends on what you mean by today. I'm gonna put an ARM research hat on. Actually, I don't even have to put a research hat on. I'll just put an ARM hat on and say, you know, there are actually quite a few capabilities, AI-related capabilities in in the architecture already, and I have a list of those in my talk. Things like bflow16, obviously we've got int8 for quantization. We have a what's it called? We've got obviously this SSV itself. There's some matrix multiplication instructions as well, dot product, etc., and of course a software stack to go with it. So from that perspective, I would say, is it complete? That's difficult to answer because I don't think any architecture is ever complete. Workloads evolve. So, but for a good range, of applications, anything we've tried, it was fine. It works. So, yeah, some of those things are architectural features that are not in hardware yet because they're just too new. However, I would say, I think we already have a great selection of features to get people started. If there's anything else that people think is missing in particular, I think we'd love to hear about it. That's for sure. But I will kind of hold up and say yes, I'm that yes over there because again, depends on how you look at today, and depends on what you're actually running. AI is an insanely large field. What type of ML algorithms are people running? Is it inference or training? Just to start with the basics. So yeah, but I'd definitely love to hear more from the other side, the non-ML side.
Mm-hmm.
Who I'm sure are embedding ML in all of their scientific applications.
Sai is shaking his head. Vigorously,
Yeah,
yes.
It's definitely a difficult situation for, I think. So this is my opinion. This is not something my colleagues will agree with, right? But I think we struggle quite a bit to find lots of AI use cases today. I think we're slowly finding them, but it's not this transformative process we're going through where AI is suddenly completely changing how we do business. I think it's more of this additive process, right? So we're still doing lots of numerical simulation. I think we're actually getting really good at generating so much data we can't actually sit down and look at it all. So we can use AI to help us with some of that, right? Machine learning kind of techniques. I don't think it's going to replace what we do. And if you think about what we do with nuclear security, I don't think you want us taking machine learning, approximations to that right now. What you want us to do is really have a very solid view that things are safe. So there's going to be, it's kind of this, how's it really going to go? But the way I think a little bit about it is, I think the hardware community, to be honest, is a little bit preoccupied with ML right now, adding loads of data type support and B floats and crazy half precisions and int8s and all this kind of stuff. Some of that stuff is useful for everybody, and that's great. But we need to be a little bit careful not to bog down our ISAs. We talked a little bit earlier about why ARM is nice because it has a lead and vector ISA. And it's important to try and not overly customize that just because machine learning is the kind of buzz thing today. Just think about what that means for support moving forward. So it's a complex answer. I think sometimes this is useful, but we've just got to be careful that it doesn't become the only thing that we worry about because we've got a lot of other business to do, at least in the world that I'm in. My gut instinct is I wouldn't be spending like tons of time worrying about how to put that into the ARM cores. I think that really this is something that a good accelerator can do really well. And tomorrow's version of machine learning will be completely different to the one we've got today. And so what we need to do is figure out how to be able to put lots of IP blocks next to each other. And ARM is really good at this, right? We've got this whole IP family, we've got all the IP blocks, we can put them all together and produce a really good system for that. So my personal view is that the ARM ecosystem is doing really well with this, and that's where we should focus, not necessarily ARM as an instruction set or ARM as a processor core IP block. This is really better put it into accelerators where customers can choose to add it to their workload, to their hardware for their workloads, or they can choose to leave it out. We'll add it, I'm sure, but whether we'd add it and it be the only thing that we do, no, we've got a lot of other stuff to worry about that actually is high priority right now. So mixed answer, I'd say.
Thanks, Sai. Does anybody else want to weigh in on this? I know this is somewhat contentious, but I think there's kind of a different split. Go ahead, John.
I was just going to say, I think that Sai's right on the money. I think there's a natural tendency for physics-based domains to want to continue to rely on the physics that they've known and understood for decades in the short term. And the gold mine, you might say, for the AI, exploiting AI at low risk is to grind through those mountains of data that the simulations are producing, or to help you with computational steering, to sample more, especially a lot of what we do in computational biology, these are statistical processes of various kinds. And, you, in a sense, when you're running a long simulation, you're sampling some of that statistical landscape. And there are some parts of that landscape that are really rare events, but they are critically important for the structure and function of the thing that you're studying. And you want to drive the simulation to study more of that interesting part that might be a rare event, and to get better sampling there. And so while you might use physics still in the core of the simulation, if you can use AI to help you get better statistics, better salient data out of what you're doing with the big machine, that can be a tremendous boon. And that's something where if the AI is wrong, it just didn't save you as much time as it might have otherwise, right? So then really, and you have still got all of your statistical and physical foundations to rely upon. So you're not going to get a wrong answer. You might have to run longer to get enough convergence or whatever statistical criteria you're after. But at least then, it's giving us a benefit right now, and we don't have to lose any sleep at night. So there's no question about, is this affecting our accuracy or something like that? So there are huge opportunities in that domain. There are also people going after, you could think of AI as sort of like, it's a lot like curve fitting or something like that. When you train something, it's kind of like using a spline to represent something rather than using an exact solution for it. And in a sense, a lot of what we do with molecular modeling, in molecular dynamics at least, we can't afford to do quantum chemistry in a time-resolved manner at full detail. These algorithms are like order n to the 12th. So we have to take shortcuts with empirical force fields. There is an opportunity to put AI in there as an alternative to empirical force fields, and people are exploring that domain. And probably that will end up being a tremendously useful adjunct to everything that's been done previously with traditional methods. And that'll mature and it'll be tremendously exciting. But no, I don't know. At this point, there are a lot of interesting trade-offs and issues, and they're exploring that now, and we don't know how it's going to all shake out in the end. It works great for the things that you see people doing right now, and but it remains to be seen, is there a limit to that? Is it memory capacity constrained? Is it memory performance constrained? The models get to be huge when you have a lot of different atom species to take care of. So we'll have to see where that goes, but there is a big application in using it as an analytical tool, or to computational steering to sample rare events, things like that. I'm a big believer in using it that way. It's very low risk. And to the question about whether or not it needs to be in the processor, I'd say watch out. Don't be another platform that uses the whack-a-mole approach and adds a new instruction today that then is at odds with your future hardware. Be careful about that. That would be my advice, because this is the Wild West right now. We're adding new instructions, like Sai said, for almost anything people can think of, which is cool. And this is maybe, I've heard about the dark silicon argument that we can afford to have a lot of specialized functional units. And so that will be a period of great exploration right now. But in 10 years, we might think back on it and say, gosh, we have a lot of strange hardware that was built in the late 2020s and early 2020s and late 2010s, and what fraction of that survives into the 2030s, I don't know.
Well, there's a good news. We control the architecture, so we can also deprecate features. So we don't have as much debt as you may think. It's actually not that bad.
Okay, great. Thank you. All right, so stay tuned. We'll probably be asking this question for the next couple of years. So I'm sure the answer will slightly change as as we see new applications for. Okay, well, my system will move. Okay, so I think we're getting pretty close to wrapping up. So I think we might have one more question after this, but what scientific challenges do you see in the next 5 years in your area that requires specific hardware or software capabilities? You know, we've talked a little bit about this, but you know, if you want to revisit or reemphasize something that you previously have spoken about, specific to your application.
Lower latency access to accelerators.
Right. Do you have any thoughts here, Andrei?
I think it's important that we keep working together. I think this has been a theme throughout this panel, and it's a good way to move things forward. We want to co-design these things to do exactly what the software wants them to do. There's no point making a processor that does something and then trying to write software that does something else and trying to match these two up. The best way to go forward is to look at what we have now, what are the weaknesses and strengths, and use that to motivate our design decisions for future generations of hardware, which I think a lot of people in the ARM ecosystem or working with the ARM ecosystem are doing, and that's great to see. That's one of our strengths, and we should keep doing that.
That's a great point. Guillaume, do you have any thoughts on your applications that you're working with? He's still muted. Okay, well, I'll open it up to anyone on the panel have any other thoughts. So we have kind of specialized accelerators, low latency, kind of collaborative design. I guess I don't know if you have a suggestion, Stephan.
Well, what I've noticed on A64FX is the availability of extremely useful performance counters that allow insight into the pipelines, etc. And so far, in my experience, maybe there are platforms that also offer this, but I haven't seen something this detailed so far, and it makes a world of difference when you are able to do manual optimization.
That's a great point. I know, we typically do a lot of local benchmarking rather than large scale simulations at my university. But we've seen this general trend to include more and better performance counters that integrate with existing APIs like PAPI. And so we started seeing some of those on TX2. And then I think looking at the A64FX, we've seen a great growth of that in terms of just useful data that you can get back about, what's that? Why is your application performing a certain way on a A64FX type chip?
And another thing that A64FX or Fujitsu, I guess, have done really well is documenting all of that. So they've published this comprehensive description of the architecture, how it works, and for performance counters as well, how to access them, which is really good. We don't usually see that much detail from other vendors, and it really helps when you're trying to understand the performance effects that you're seeing. It's very nice to be able to relate back to reference on how the chip actually works, instead of just treating it as a black box and trying to learn things about it by poking it from various sides.
Okay, great.
Yeah, I'd agree with that. I think one of the things that we'd like to see a lot of is just a really good focus on trying to get, I don't know how to describe it, but like cross-vendor things for protocols and for the hardware links. We talked about the low latency accelerators. We're completely behind that too. Some standardization around that, perhaps with things like CXL, but maybe some future generations of that, so that it really can become a plug and play for everybody's different workloads. I think that's a big deal, right? And that can help with very clean software design, that we can write our applications and our libraries once and they can run across lots of different hardware types. You know, that stuff's a real challenge today because every vendor has got their own version of everything and it all does completely different things in different ways. And the net effect of that is I think we just give up and we just concentrate on a few of the vendors and try to do a really good job with those. So really just focus on standardization. It'd be a massive help to the community. You know, Arm's really good at that. Other vendors are getting better at it. And I think that if we can move to that, we'll end up with you know, some really optimized hardware nodes, and that will be great for us.
Jeff, you're muted.
Sorry, thank you. I'm jumping ahead real quick. Thank you for the nice answers. So we had a few questions for the panel. I'm not sure we really have anybody who's an expert on LLVM here, so we might.
I can answer that one.
Yeah.
LLVM supports SV, or I think maybe it's planned for support SV, but I mean the Arm HPC compiler supports SV. Arm.LLVM supports because people have been using Arm Clang, and then you've got yeah, so it supports SV already, and I can briefly talk that int8 already is a data type that's supported. I'm not sure if int1 will be very useful. I'll be honest. Int4 I think is a debatable one, but yeah.
The LLVM backend supports SVE. Clang doesn't for now. So as far as I'm aware, if you grab the latest Clang LLVM source code, you won't be able to compile a C program from start to finish to an SVE target. But I think support for that is planned for sometime next year. There's lots of work going on. Lots of work that's in progress, and eventually it will be merged. Lots of vendors are interested in this because pretty much all the compilers for ARM CPUs are based on LLVM in some sense. So that's true, obviously, for the ARM compiler, but also for Cray's and Fujitsu's compilers, both of which target SV.
Great. And you know, I think we've got to wrap up here, but just if you'd like to speak about your application, are most HPC AI workloads compute bound, or is this, you know, HBM that we're seeing on new systems, is that kind of a critical aspect, or, you know, do we just need to see really, you know, processors with really big caches? I don't know if any of you quickly want to speak to that.
We just did a real quick study on our Crossroads procurement, which is a machine we'll put down Los Alamos in 2022-23. About 50% of that workload was compute bound, and about 50% of it was memory bound. Compute bound isn't all floating point, right? We do lots of integer calculations to think about addresses and where we've got to go find operands. So that's mixed. Think about int and FP. It's about half and half, basically.
And based on the applications that we see people running on Archer, the UK's national supercomputer, a lot of it is memory bandwidth bound. The mini apps that we use at Bristol mirror these types of workloads very well, and most of them are memory bandwidth bound. Some of them are latency bound, so it's good to have fast caches, but if it takes a long time to get to that data, that can also hurt performance. And in most cases, even though you are mostly bound by memory bandwidth, you can't completely neglect integer performance, like Sai said, because then a lot of the stuff that needs to happen to get that data takes a long time, and that hurts as well.
Okay. Great. Well, and I think we've kind of talked about the different instructions, and it seems like in my understanding that there's interest in future data types, but as long as we don't, you know, as long as we don't complicate the ISA too much. So I'll let folks talk with Roxana and others offline about that. Thank you to all our panelists for joining today. Thank you for submitting videos. I'd like to encourage all of our attendees to go to our YouTube channel There are lots of great talks. I think we actually added a few towards the end of last week, so we're up to about 30 really excellent talks. Thanks to our ARM colleagues for helping us to organize this. Unfortunately, I don't think there's a Birds of Feather SC this year just because of the pandemic. But this virtual event, the panels and the videos are kind of letting us fill that gap a little bit and share recent results and ask some really good questions like we've done here today. Okay, thank you everybody. And hopefully we'll see you online or maybe in person next year.